Hey there, everyone, and welcome to this first lesson on further mathematics. So we're going to be beginning with algebra, and in particular, today we're looking at advanced number theory and how that ties into algebra. So here we've only really got two things we're going to be looking at today. We've got the product rule for counting, which is about how many different ways can you count something, or more, it might be better thinking of it as how many different combinations of something can we have if we've got a certain number of items, how many different ways can we combine them, and what's kind of like logic for how we would calculate that. And then we're going to be looking at algebraic proofs, which is when we might want to be proving some kind of statement about numbers and how we can then express those numbers through algebra to then prove those things to be true for all particular values that we're interested in. So that's the general idea what these two things are. So let's take a look at product rule for counting first. So what is this? Well, let's take an example like this where we have four slots. Like imagine we're trying to pick like a pin number for something, and one example could be something like this where we've got the digits from 0 to 9 are our possibilities for each of them, and we want to know how many different combinations could we make there. And well, here's our options. So we've got the numbers 0 to 9. So important thing to note there that is going to be then 10 possible digits. Some people might think it's 9 because you're counting 1 to 9, but no, you're including 0 as well. So it's going to be 10 possible digits. So the number of combinations that we can do here is we take the number of possible combinations for the first, times by the number of combinations for the second, times the number for the third, and then the fourth. Hence why it's called the product rule, because we're taking a product of the number of combinations for each. So the total number of combinations will be this: 10 times 10 times 10 times 10, because we've got 10 options for each. And so in total, there'll be 10,000 possible numbers we could make here. Like, say, like I said, if we were picking a pin number or something, there'd be 10,000 possible pins we could create. So that's a simple, first example. Um, Oftentimes we'll have constraints that we have to deal with. So this scenario that we have here, you can see we've got a repeat number, like a duplicate number of 1. The 1 is repeated uh, in the third and fourth slot. But imagine if we don't want any duplicates. We want each number to be unique. So it'd be, say, something more like this. How would we then account for that? How can we then calculate how many combinations there are? Again, what we'd do is we'd go through each digit at a time. They don't even necessarily have to go in order, but we consider one digit at a time, and then we see how many options do we have for each, considering what we've already selected. So for the first digit, say if we just go simply left to right, the first digit, we have 10 options, don't we? 0 to 9, same as before. But if we're not allowing repeats, when we then go to the second digit, we now have one less option. So in this case, say if we pick the 3, we now don't have the 3 to choose from for the second digit. So we now actually have 9 choices for the second option. Um, and then in this scenario here, we picked a 5. So when it comes to the third digit, we can't pick the 5 now either if we don't want any repeats. And we continue on for the fourth digit, we can't have the 1 because that was selected in the third slot. And so we can see the number of possible combinations here, again, applying this product rule, is going to be this. So we see 10 options for the first, 9 for the next, 8 for the next, and you see it just gradually goes down like that. And we work that out, it's going to be 5,040. So it almost halves, really, the number of choices that we have if we don't allow repeats. So that's one common thing to consider is, do we allow repeats or do we not allow repeats? You've probably seen this a little bit before in probability when you're calculating the probability of multiple events, like are they independent events or dependent events? You can think of it like that. Are they independent or dependent? In this case, they're dependent because whatever we pick in one slot affects the next one. So yeah, it's a very similar concept, and this study of combinations, product rule for counting, has very useful applications in probability. So now let's take another example. It's a bit more complicated still. So we're considering another 4-digit number. But the constraints we have this time is, first of all, we're told that the first number is going to be 7. So the first number is going to be absolutely 7. We know what that one is. And we're told that the number as a whole is going to be even. So we have something, say, like this. This would be one example of a number that we could produce where the first digit is a 7 and the number overall is even. And we want to consider how many different combinations there are for this. So we need to think, how is this going to affect the choices that we have for each number? So this is where a little bit of number theory has to come into play. Like you think about, okay, what makes a number even? And you've probably heard of this before, that an even number is going to be simply determined by the last digit. If the last digit is even, then the whole number is going to be even. And so if we consider that last digit for a moment, we don't have 10 options. We've only got 5 options. We've got 0, 2, 4, 6, and 8 is what that last number has to be in order for this whole, 4-digit number to be even. So now we can start working out our combinations again. So we know that one needs to, we have 5 options. So we'll have a 5 for that last digit. For the first digit, we're essentially just going to have the number 1. So times it by 1 doesn't change anything because we know it's going to be a 7. And then the remaining 2 are just going to be 10 each. We're not worrying about duplicates at the moment. We're just considering, each one could be the numbers from 0 to 9. So the total number of combinations is going to be this. We've got 1 option for the first. The next 2 could be any number. So we've got 10 options for each. And then the last one only has 5 options. And so what we'll find is we have 500 combinations that we can make given these constraints. So now let's consider it when you don't allow for repeat numbers. And so this is where it can get a little bit tricky when we've got kind of more specific constraints going on and you're not allowing for repeats, and we need to think about how this is going to affect things. So again, you see this number here, we've got repeats at the moment. We've got 2 6s. So say if we have a number like this instead, where this would be an example of a number that fits the criteria, where the first number is 7, the overall number is even, and we're not allowing repeats now. Now let's try and find how many possible combinations we can do. So it gets a bit trickier because, okay, the first number has to be a 7. So that's fine, just one option for that. But then what about the next 2 numbers? Would we maybe then times it by 9 because we've already picked the 7? So there's 9 options for the next, and then maybe 8 options for the next because we've already picked the previous 2. But then what happens to the last one? Because, okay, we have 5 options because it's even, but it depends on what we've picked before. Especially those 2 previous numbers we picked. If it was an even number, it's going to reduce that count by 1. If it's an odd number, then it's not going to affect the count. It will just remain at 5. And so that becomes a bit tricky. So this is when you want to change up the order. Maybe think of that last number first. Imagine we're picking that first number first because we're not insisting we have to pick left to right. We're just picking 4 digits here. So if we do that last number first, we've got 5 options for that. We pick the first number. Well, there's only one option, it has to be a 7. And now we pick the remaining 2, which will then be 8 options and then 7 options because we've already picked the first number and the last number. So we've already picked 2 numbers. So there's 8 left for the second number and then 7 left for the third number. Or you could do it the other way around if you wanted to, but it'll still work out the same. So yeah, the total number of combinations will be this. So by doing it that way, we can then be sure we don't get these ambiguous scenarios where for that last digit, we don't know, is it going to be 5? Is it going to be 4? Is it maybe only going to be 3 choices? And you wouldn't know. So by being changing up the order in which we're selecting them, we can then get a specific number like this. And we find it's 280 options. And we've got there. So yeah, a little bit of a trickier one, that. But that's the way you want to approach it when you've got this kind of interplay where one number can affect the number of combinations for the other. So let's move on. Right, so let's take some kind of real life scenario here. So there is a shop that offers a variety of combinations of sandwiches and drinks as part of their meal deal. And we know there are 12 different types of sandwiches that can be part of the meal deal. And we also know that with the drinks, we can make a total of 168 combinations. Um, and what we want to do is then use this information to find out, okay, how many uh, different types of drinks are there offered as part of the meal deal. So this is a little bit different. So rather than being given the numbers of things, like the number of sandwiches and the number of drinks, and we're trying to find the combinations, we've been given the number of combinations, and we're trying to work our way back to finding the number of drinks, this unknown number. So whenever you have something like that should be telling you that you probably need to use a bit of algebra here. So let's say if we let x be the number of drinks, that we're trying to find. And now we can use what we've just learned a moment ago, that the number of combinations we can make is going to be simply the number of sandwiches times by the number of drinks. And so we form a little equation like this. 12x is going to equal to 168, because 12 being the number of sandwiches, x being the number of drinks. And we can solve something like that quite easily. Just do 168 divided by 12, and we get 14. So there we go. So it would be as simple as that. If we're not worrying about, repeats of combinations, then yeah, it would just be as simple as that. So yeah, if you make sure you understand this product rule, we can easily form an equation like this when we've got the number of combinations and we're trying to get back to the actual number of items. Let's take another example like this. Well, not an example. What we're trying to do now actually is form a general formula to calculate the number of unique ways of choosing some number of items from a total number. So in this case, we want to pick R number of items from a total of N number of items. So this is a formula that you might have seen before. What we're going to do is going to gradually build it up logically. So hopefully this formula will make a lot more sense to you, why it works, as opposed to just how to use it. So since we've already seen the way we can arrange n items, it's just going to be this. So if you imagine, say, if you had three objects and you want to see how many times you could rearrange them, well, you're going to have basically three options for the first one, two options for the next, and then one option for the last. And so what you do is you end up getting 3 times 2 times 1, and it works its way down to 1 like that. And that's going to be the same for any number of items. So for a general n number of items, you're essentially 1 times 2 times 3 all the way up to n, if we just change the order around. And this has a special notation in math. We call this a factorial, which is denoted with an exclamation mark. So when we do n factorial, it means do 1 times 2 times 3 all the way up to n. So that word is spelled like this. So factorial is an important word to be aware of it here when dealing with combinations. So now, how can we now adjust this expression to instead not calculate the different way of arranging n things? It's like, how many different ways can you select n things out of n things? But we want to know how many different ways can you select r things out of n things. Which, what we need to do this. We divide it by n minus r, because if we're selecting r number of things, that means there's going to be n minus r number of things left over. And so we need to essentially divide that away, and it takes that out. And that's like what we saw a moment ago when calculating the number of ways of picking a 4-digit number. We didn't do 10 times 9 times 8 times 7 all the way down to 1, did we? We did 10 times 9 times 8 times 7. And then everything from 6 downwards essentially gets removed, because we're only selecting 4, we're not selecting 10. And so that's essentially what this formula is doing. So yeah, you might want to try this out for a few different values of n and r, and you'll be able to see that's what's going on here. Like the example before, what we essentially did was 10 factorial over 10 minus 4 factorial, and you'll see that the math works out there. So that's what's going on there. We're now building this up into a general formula. And then one last thing we want to consider is how can we now adjust this expression to remove all combinations that are simply repeats? So, like I kind of mentioned a moment ago with the whole meal deal question we had, you might have one combination could be, say, something like, I don't know, a cheese sandwich and a Coca-Cola, and you'd have another combination would be a Coca-Cola with a cheese sandwich. But you notice it's essentially the same thing, isn't it? We've just swapped the items around and say we don't want that. We just want the unique combinations. We don't want ones where they've just been swapped around. Well, then we have to do this. We divide by the number of ways of arranging those R items. So with two items, it's quite simple. There's only two ways to organize them. But if it was a larger number, then a R factorial would be the number of ways of rearranging them, wouldn't they? So this ultimately is our formula. So if we wanted a way of picking R items out of a total of N items without any repeats, like any like combinations that are just simply repeats of another, but just in a different order, then this is the formula we use. And it's often denoted like this, NCR. And you can see this on your calculator. You might want to work out for your particular calculator how you can use this. And it will very just quickly allows us to um, uh, calculate the number of combinations like this. Sometimes it's also denoted like this, almost like a vector, where we've got NR like this, number of ways of choosing R things from N items. So let's try an example of applying that. So say a situation like this, if we've got a pizzeria that offers 10 different toppings, and suppose we want to order a pizza with 3 different toppings, how many different pizzas could we order? So here's an example of, like, say, a pizza we could have, and the 3 toppings that we have on it. So we've got pepperoni, we've got peppers, and we've got onions. But we don't want any repeats. Like, say, if we had this combination, which is peppers, onions, and pepperoni. You see, it's the same pizza, isn't it? I've just changed the order of the toppings. So we don't want that. So you see, we're choosing 3 toppings out of a total of 10 toppings, and we don't want any repeats. We want to see how many unique combinations there are. Well, here is a prime example of where we could use that NCR formula. So here we have N is the number of toppings to choose from, R is the toppings that we're choosing, and we can see that's going to be 10 and 3 respectively. And if we plug that into our formula like this, and if you've got a calculator, you could just put this into your calculator, either the fraction there or use the NCR function. If you had to do this on paper, this is actually not too hard to work out. If you write this out in full, like 10 factorial across the top, and then we've got 3 factorial and 7 factorial on the bottom, you would notice that there's a lot of factors we can cancel out here. For example, say the 7. We've got a 7 on the top and the 7 on the bottom. Like, this is just a product across the top and bottom, so we can easily cancel out factors. But you see, we can continue with the 6 as well, and the 5, and the 4, and 3, and 2, and 1. Like, they all cancel out. So straight away, we've already simplified quite nicely to this. But we can need to go a bit further as well, because notice that the 9 will be divisible by 3, the 8 is divisible by 2, so we could kind of cancel out those factors there. The 9 would become a 3 and the 8 would become a 4 if we take out those factors of 3 and 4, cancelling out with the bottom. And now this is a very nice calculation. We can work out quite easily. That's going to be 120. So yeah, if you ever had to work this out on paper, that's the way you would do it. Otherwise, it would become a very horrendous calculation. You want to make sure you're cancelling out those factors. So yeah, there we go. 120 combinations is the answer to that. Right, so let's get moving on to algebraic proofs. So this is a whole other topic separate from the product rule from counting. And here's an example of something we might want to prove. Prove that the sum of 2 even numbers is also an even number. So how would we use algebra to prove this? So what we need to do is we need to take an even number and try and represent that in the general sense using algebra. So say if we take a number, A, and we say A is just any integer. Sometimes how we denote it is like this. like this Z symbol is often used to denote the set of all integers, and that little funny symbol that looks like an E is basically like saying A is in the set of all integers. So you might sometimes see this notation. It's not so common. This is basically saying that A is an integer. Well, integer, that basically means a whole number, isn't it? But an even number is specifically an integer that's divisible by 2, isn't it? So what we could do is create another number that is simply 2a. Because if a is just some integer, like a is either 1, 2, 3, 4, 5, so on, well then 2a will be either 2, 4, 6, 8, 10, wouldn't it? So here we've found a way to write an even number algebraically. And we could do the same thing for another number. So if we have some other number, other integer more specifically, and 2b will also then be an even number, but another even number. And now we can start to prove this statement here. We want to show that the sum of these two numbers will also be even. So the sum of these two is going to be 2a plus 2b. So in order to show this is even, what we need to show that explicitly there is a factor of 2 in this number. And we can do that by just, well, factorizing out the 2. Like that, and that's the end of the proof. And when we finish a proof, sometimes we put this little like square at the end. It signifies end of proof. Like you don't have to do that, but that is like what mathematicians normally do. And what's normally good as well is to finish up your proof with an actual sentence explaining what's going on. And what I would say is something like this: like after summing the two even numbers, you see that the end result we get, we can take out a factor of 2. And if we can take out a factor of 2, that means it's divisible by 2, which means it's therefore even. So there we go. That's how we prove something like that. So that's the key. What you want to do is take the numbers in question, write them algebraically, and then do the calculation and show what you're trying to prove there. So in this case, proving it's even means we need to be able to take out a factor of 2. Let's take another example. So prove that the product of two odd numbers is also an odd number. Well, we can set up an odd number in quite a similar way to the way we set up an even number. So we take, say, some integer a, and we know that 2a will be even. Therefore, 2a plus 1 would be odd, wouldn't it? So if 2a is going to represent some even number, if we add 1 to an even number, it's going to necessarily become odd, isn't it? So we've got a nice little expression here that will prove that will always be an odd number. This will in fact be all odd numbers. So you take if a is 1, 2, 3, 4, so on, 2a plus 1 is going to be 3, 5, 7, 9, and so on. So you see this will represent all odd numbers. And we do the same thing again with a different integer, b. 2b plus 1 will then also be odd, but another odd number. And now what we want to do is show that the product of these two numbers will also be odd. So this product, we want to show that that's always going to be odd. So a good place to start here would be to expand it out. And then what we do is remember algebraically, what does it mean to be an odd number? It means essentially we want to show it's going to be one more than some multiple of 2. Well, we see we've got that plus 1 there. Is the remainder of the expression a multiple of 2? Well, it is, because look, we can take out a factor of 2 there, can't we? The 4ab, the 2a, and the 2b all have a factor of 2 that we could take out. So we can see this number here is basically 2 times some number, which is going to be even, plus 1. Therefore, it's going to make it odd. So that would be the end of proof there. We've managed to show that that is going to be an odd number. Doesn't matter what a and b are, it's necessarily going to be odd because it's one more than an even number. And so, yeah, we'd have a final statement again to explain this. After multiplying the two odd numbers, we get a number that is one more than a multiple of 2. Therefore, it must be odd. So that's how we would prove that. Right. So let's take something a bit trickier now. So there's not a huge number of things they can ask you about algebraic proofs. You got even numbers, you got odd numbers, and showing it's divisible by something. Like we've seen that showing it's divisible by two means taking out a factor of two. Well, in this example here, where we need to prove something is divisible by three, it's going to be a similar thing, but we need to be able to take out a factor of three. But the question is asking to prove that the sum of three consecutive numbers will always be divisible by three. So how do we write that algebraically? Like three consecutive numbers, what that going to look like? Well, what we don't want to do is something like this, where we do, A, B, C being three integers, and then we do A plus B plus C. That's not really going to get us anywhere. Like, how are we going to show that that's divisible by three? And the answer is we can't, because what we've done there, we've just taken three arbitrary integers, like any three integers, not three consecutive ones, which is what we actually want. So how we would do that is instead take a single integer, which, say I label that x here, and think about consecutive. Consecutive meaning directly next to one another. So the next one would be x plus 1. And the next one along from that is going to be x plus 2. Those will be consecutive numbers. So our three numbers we could write like this instead, which is a lot better. We're encapsulating that information of being consecutive in these algebraic expressions. And so now we're kind of in a place to show this, because, okay, let's add all these up and use your algebra skills to collect together your like terms there. And you see we end up getting 3x plus 3. And you might be able to spot now, well, there's clearly a factor of 3 there that we can pull out. It's 3 lots of x plus 1. So it doesn't matter what x is or x plus 1, because we see there's that factor of 3. And 3 multiplied by any number is necessarily going to be divisible by 3. So that's end of proof there. And again, you might want to write a little statement. It'd be along the same lines of what we've seen before, just sort of saying because we can take out a factor of 3, it must be divisible by 3. Right. So now let's move on to some ones more to do with almost like a function. So say if you got something like this, and we want to prove that this function of n is a square number for all integer values of n. So that's another key word to be aware of there, square. So what does square mean? So a square number means a number that can be written as some other number squared. So for example, 9 is 3 squared, so 9 is a square number, or 49 is 7 squared, or 100 is 10 squared. These are all square numbers. And what we could do, first of all, is we could plug in a bunch of different values for n, like do n equals 1, n equals 2, n equals 3, and evaluate it out. And you see, indeed, it does look like all the numbers are square. 16, 9, 4, 1, even 0. 0 is 0 squared, so that's still a square number. But this isn't proof. This doesn't show it for all values of n, and we can't list all values of n, can we? Because it's like infinite. And there's been many, famous theorems in the past where they've been proven true for like the first 100,000 terms, and then suddenly it stops being true. So even if it looks like it's true for a while, we can't assume that. So how do we actually prove this for all values of n? Well, what we could do is, so remember, a square number is basically a number that can be written as another number squared, so another number times itself. So you think about it, when we take something, especially something like this, what we notice is this is a quadratic expression, isn't it? And you think about, okay, how do we write a quadratic as the product of two things? Well, that's factorization, isn't it? So why don't we try that? If we try factorizing this using, your standard techniques for factorizing, what you'll find is you'll get n minus 5 times n minus 5, which is equal to n minus 5 squared. And that's end of proof, isn't it? So because it doesn't matter what the value of n is now, we've shown that this expression is going to equal to n minus 5 squared, which is necessarily going to be a square number. So there we go. That's how you would approach something like this. You need to you want to try and get it into that form of something squared, because that will necessarily be a square number. Typically, you'll be asked something like this where it's a quadratic, and so it's mostly involves factorizing it. Um, and again, you might put a little statement at the end. If n is an integer, therefore n minus 5 will also be an integer. And the square of an integer is, by definition, going to be a square number. A little sentence like that will then wrap up this proof nicely and get you full marks. So, good. I'm hoping that's all making sense. So let's tackle, I think, one last example. So this is something now, a kind of more advanced problem you might encounter would be to prove something like this. Prove that this expression of x is always going to be greater than 0 for all values of x. And again, we could go through a bunch of different values of x. I've taken integer values here. But notice here, we're not looking at integer values of x. We're talking all values of x, even fractions and irrationals and all that. So, in these examples that I've done here, it looks like it's true. All the numbers coming out on the right-hand side are all greater than 0. So it looks like it's true, but how do we prove this for all cases? So, if your first thought is maybe we should expand out and collect like terms on the left-hand side to see precisely what equation we've got here, that would be a good instinct to follow. So say, first of all, that first bracket of 3x plus 2 squared will be this, wouldn't it? 9x squared plus 12x plus 4. And the second bracket, if we expand that out, you'll get this. And we want to see, is that greater than 0? That's the question. So how would we do that? Well, let's continue on. Collect like terms. You see, this is going to cancel out quite nicely. See, the 9x squared and the minus 8x squared is just going to be x squared. 12x minus 12x cancels out, and we're just left with the plus 4. Now, if we try and rearrange this like this, that gets us the end of proof. This proves the result, and you might want to pause and take a quick look at this and try and work it out for yourself why this proves this to be true, why this statement is always going to be true. Otherwise, let me explain it. So remember, when you square something, regardless of what the number is, it's always going to produce a positive number, isn't it? So a positive number squared is going to be positive. But a negative number squared, like a negative times a negative, will also be positive, won't it? So therefore, we know this statement is always going to be true because x squared will always be positive. And if it's positive, then it must be greater than minus 4. So this is going to be true for all values of x. And so therefore, our original statement must also be true for all values of x, because all we've done is a bit of algebraic manipulation here. So that's how you would prove something like that. And again, finish up with a little statement. You say the square of any number is always positive and therefore must also be greater than minus 4. And so if it's now true for all values of x. So, a bit of a tricky one there, but you see, it's a matter of just really understanding different keywords, like, and how to express them algebraically, like even numbers, odd numbers, consecutive numbers, square numbers, and really being able to analyze an expression like this x squared greater than minus 4, and to be able to see that is always going to be true. So yeah, let's leave it there. So here, I like to always finish up with a challenge question. So this is something that is really pushing you to kind of limit the syllabus, or perhaps even a little bit further. You know, it's more for you guys who just want a real challenge, but you might not necessarily expect something like this in your exam. So here's an example of prove that the expression of n cubed minus n is going to be divisible by 6 for all values of n. So this one is, you can use some of the techniques that we've seen in today's lesson, but it's not quite as clear cut. And I've given you a few tips here of how you would approach this problem. You might want to first factorize the expression. You could take out a factor of n to get you started. And then you want to notice, once you've fully factorized it, you're going to get 3 factors, and try and look at how those factors are related to one another. consider the divisibility of those three factors and see if you can then logically explain why this is always going to be divisible by 6. So yeah, quite a tricky one this. So yeah, well done if you can get it. But yeah, don't worry if you can't, because like I said, this is designed to be a real challenge. So here's your takeaways for today's lesson. We next time we're going to be continuing on with algebra. We're going to be looking at functions and looking at functions in a bit more detail than you would have done in your regular GCSE syllabus. So I'll see you next time for that.